This video will introduce our recent work, a Parse-Then-Place approach for generating graphic layouts from textual descriptions, which is the first text-to-layout work. Graphic design is ubiquitous in our daily life. Layout, the sizes and positions of design elements, is fundamental to a graphic design. However, creating layouts is a complex task that requires design expertise and consumes much time. While we may not have design knowledge and be unfamiliar with design tools, we have a strong linguistic ability to express our requirements. Thus, in this work, we propose to use text as the guidance to create graphic layouts. While automatic layout generation has been intensively studied, text-to-layout is rarely investigated and remains a challenging task due to its unique way to specify layout constraints, including implicit constraint, combined constraint, incomplete constraint, and scarcity of labeled data. To tackle the challenging text-to-layout, our intuition is threefold. First, we can take advantage of pre-trained language models to transform implicit layout constraints into explicit ones. Second, generating layouts conditioned on explicit constraints is a well-studied setting in prior work. Its success motivates us to take the same formulation and seek a way to represent combined and incomplete constraints in text-to-layout. Third, graphic designs are ubiquitous and their layouts are often abundantly available, which are highly valuable for learning to generate high-quality and diverse layouts. Based on our intuition, we introduce an intermediate representation between text and layout to formally represent diverse layout constraints, such as element type, size, and hierarchy. By introducing IR, our approach decomposes text-to-layout into two stages, parse stage and place stage. As a bridge between text and layout, IR should meet the following two requirements. The first one is expressiveness. It means that IR should be expressive to represent diverse user constraints on layouts. Otherwise, the mapping from text to IR will incur undesired information loss. The second one is formalism, on which the existing natural language understanding techniques can exhibit accurate understanding performance. Then, the parse stage maps a textual description into an IR, where implicit and vague constraints are transformed into explicit ones. It is similar to a natural language understanding problem. Hence, we fine-tune T5, a transformer encoder-decoder based model to address it. The goal of the place stage is to generate a layout according to the constraints specified in IR. Inspired by Layout Former++, we formulate this stage as a sequence-to-sequence transformation problem and adopt a transformer encoder-decoder based layout generation model to solve it. To represent combined constraints, we serialize each constraint as a subsequence and concatenate all of them in a certain order. To facilitate the model learning to complete omitted elements given incomplete constraints, we introduce a categorical attribute for each element to indicate whether it is auto-completed or not. It helps the model better distinguish the auto-completed elements. Graphic layouts are easily accessible in the wild. Though they do not have corresponding textual descriptions, their wealthy layout patterns are tremendously helpful for acquiring layout generation skills. Therefore, we attempt to pre-train the layout generation model with large-scale unlabeled layouts, and then fine-tune it with labeled data. Specifically, for pre-training, we curate a synthetic dataset from unlabeled layouts, where IR is synthesized from layout, and we use it to pre-train the place stage. After pre-training, we fine-tune the model with labeled data to close the distribution gap between synthetic and labeled data. There are two main reasons for this gap. First, the characteristics of elements that are commonly omitted by users cannot be perfectly described in the synthesized IR. Second, position and size constraints are subjective. The quantitative results show that our method significantly outperforms the baselines on all metrics, indicating that it can generate layouts that are more visually pleasing and consistent with the descriptions. Moreover, our method can generate layouts with similar or even better alignment and overlap compared to real data. The qualitative results demonstrate that the layouts from our approach are of high quality, while the layouts from baselines frequently contain misalignment, incorrect overlap, and weird spacing. Besides, the layouts from our approach are more consistent with the descriptions. Our approach can also complete omitted yet important elements. Moreover, our approach can generate diverse layouts with rich patterns and high quality, while other methods either suffer from unsatisfactory quality or homogeneous layout designs.